the talk.
Thanks for tuning in.
Definitely.
Cool. Okay, very good. Welcome everybody to the first Shocklab talk, actually in a little while, I guess. Nice to get things started again. So we are very, very happy to have Callum Tilbury here today, who is a senior research engineer?
Research engineer.
Research engineer. Not just a research engineer, but a research engineer at InstaDeep. So Callum did his undergraduate here at UCT in the electrical engineering department, and then went overseas to Edinburgh. His first overseas trip, indeed, in the middle of COVID. An interesting experience to go and do his master's with Stefano. And some of the work that he's been doing now is sort of a natural lead on from that. Callum is not only an RL expert, but also is a musician and a photographer, and he has a blog, which I didn't know about until recently. So you can check that out. But yeah, today he's going to be talking about some work that I've been involved with, but really Claude, Louise, and Callum and Anu as well have been working on about coordination failure in offline. Over to you.
Cool. Thank you, Prof. Shock, for the warm welcome, and thank you everyone for being here. It's so nice to talk to you, and yeah, happy to talk about this work that we've been doing. I'm just going to close the door. Yeah, and thank you to those online as well for joining. Please interrupt me at any point as well. Just raise your hand if you have a question. Really happy to field those. And yeah, so we're going to be talking about coordination failure in cooperative offline mile. That's a lot of words. I'll explain each of those words in time. And I've also just put this diagram as a kind of a little preview. You don't have to understand it just yet. We'll dive into it a little bit more. Just to provide some problem context first. We're asking the question, what happens when we're trying to learn multi-agent coordination? So coordination kind of naturally arises in multi-agent scenarios from a static data set. What does that mean? What does multi-agent coordination mean? Here we have what is called robotic warehouse. And the idea is that you have little robots, so these little red and yellow things that are moving around a grid world. So you can imagine kind of the floor of an Amazon warehouse. And in green there, we have packages that arrive, right? And so suppose you order a new hairbrush from Amazon, and this robot needs to go fetch it, pick it up and take it to the depot on the right-hand side there, right? Now, ideally, what we want to do is formulate this as a multi-agent problem, such that we can have multiple robots operating in parallel, right? That's more efficient and allows us to kind of have high throughput. The challenge there is, what if your robot crashes into another one? Or more importantly, how do we make sure that it's efficient? So that if you're close to a package, you grab it and you don't have to go to the other end where perhaps there's another robot there, right? And so naturally, we have this idea of coordination that naturally arises from the multi-agentness of this problem. And so that's kind of the focus of what we're doing. And what is a static data set? Well, the idea here is that we don't necessarily have access to the simulator itself, and we don't have access to what's called online experience. So we can't actually test our policy or kind of the way our robots are going to act in the real world or even in a simulator. Instead, we have this data set, which I've denoted as B. And this data set is just trajectories, recordings of times in the past that these robots have operated. So here we have a bunch of examples of the robots doing various things. Now, this might have come from some sort of, maybe human demonstration. So a human might instill policy by saying, okay, this is how we think that it should act, or maybe they're random policies, or maybe they're trained policies. But for some reason, somehow we have, we know what the reason is, but somehow we have this static data set, and static just meaning that it's offline. We're not interacting and generating new dynamic data. We just have this data set, this storage of data B. So what happens when we're trying to learn multi-agent coordination from this static data set? Just as a quick primer to take a little step back, we're not going to get into the depths of the maths around reinforcement learning, but I just want to kind of explain the gist of it. So we have this agent, Mario here on the left. Sorry, no copyright infringement intended. We have Mario, our agent, and the way the reinforcement learning loop kind of works is that Mario exists in this kind of state, and he gets observations from his state. So, for example, here he sees that he's kind of in space. You can actually see him in the bottom left-hand corner there. And he might have some sort of observation about his environment. And he takes an action in that environment. So perhaps he moves forward. And he has some sort of goal. So, maybe there's an example, which is getting a coin might be a good thing, right? So he moves around this environment. He takes actions. And in each action he takes, he gets a new observation, and he also gets a reward for what he's done, right? And so maybe he steps on that nasty thing there and he gets a negative reward. In other words, he actually shouldn't have done that. Or maybe he jumps up, that's his action, and he gets a coin, and that's a positive reward. And that's kind of the reinforcement learning loop that happens in discrete time steps. Well, what is multi-agent reinforcement learning? Now we have Luigi, right? Luigi's here as well, and he's also running around. And so now we have actions, multiple actions. Mario might move forwards, Luigi might move backwards, right? And the challenge here is, of course, what Luigi does impacts what Mario does and kind of his observations and the rewards he gets, right? Because it changes the environment. As Luigi operates in the environment, Mario has to kind of understand what Luigi is doing. And so that's why it's a lot harder. So we have actions, sets of observations, and potentially multiple rewards, right? That's the multi-agentness of this problem. Now, what is offline multi-agent reinforcement learning? Now we have this data set again, B, right? See, we kind of have cut off access to the simulator. We don't have that Mario Luigi environment anymore. We can't test out what is it like to kind of jump up and get that coin. We just have a data set of recorded experience. So perhaps at some point in the past, Mario was running around, Luigi was running around, and we recorded that. Now we're trying to learn from that, right? That is the offline multi-agent reinforcement learning problem, kind of at a high level. And I'm just going to bring up this question again. What happens now when we try to learn multi-agent coordination from the static data set? So how can we get Luigi and Mario to actually coordinate when all we have is the data set itself? To explain why this is difficult, I'm going to present an idea called a polynomial game. And we don't have to worry too much about the maths, just that in general, we can write kind of a polynomial of x and y. So a very, very simple example is x times y. And this r is essentially the reward. So now we have two agents. Imagine agent x is Mario, and agent y is Luigi. And all they can do is choose a scalar number, right? So Mario, for example, could choose 0, and Luigi could choose 0. And that would naturally, in this game, yield a reward of 0. And equally, Mario could choose a positive number, and Luigi could choose a positive number. And hey, that's a high reward, right? That's a positive reward. And that's that yellow region in the top right-hand corner, right? And you can imagine all sorts of other reward combinations. I don't have to enumerate them all. But essentially, we have this continuous reward surface, right? Defined by the action that agent X takes, X, and the action that Y takes, which is Y. And so in this case, it's the product of their scalars. You can imagine all sorts of other polynomial games. Some minor details, it's stateless, which just means we only exist in this state. And so, Mario takes his action and Luigi takes his action, but it doesn't progress to a new game or anything. That's kind of just a reinforcement learning point of clarity. It's a stateless game. It's also atemporal, so it doesn't exist over time. They just take their action, and that's kind of the game. And then we're just sort of going to assume that they can access a perfect kind of knowledge of this reward surface. And that's not too important for kind of the essence of what we're trying to get across. Here, what we're saying is that the agent policies, now, typically in deep reinforcement learning, we're going to kind of have the agents using a neural network to decide what to do, right? So we're going to have a deep neural net there as their parameters, theta x and theta y, and that might be very, very complex. Here, we're just going to make it super simple. We're going to say that mu x, which is kind of the action, the policy of agent x, is just theta x. So just the policy is the parameter itself and the action that it takes. So x, when it chooses 0, that means that its parameter, theta x, is just 0, right? And that just simplifies the mathematics. But we do note that as we get into kind of more complex situations, that theta x might be, parameterized by a deep neural network. Now we get to this idea of coordination failure. Do we have any questions about kind of just the problem setup up until this point? If we don't, it's completely fine. You can just shout whenever you have a question. So, yeah.
Why is S0 0?
Yeah, so it's stateless, and what we say is that here's just a linear layer that's dependent on the state, but hey, we can make the state whatever we want. Let's make it 0, and it simplifies the maths. That's a good catch. Cool. We're going to get into this diagram. So kind of have 3 things, and I'll deal with them each in turn. And the important thing here is that term at the top right, which is BRUD, right? Best response under dataset. And that's going to become quite important. So suppose now we have our agent policies, right? Which is, again, theta x and theta y is just what are the agents doing right now, okay? So theta x is currently parameterized to take a negative action, right? So if we look at this x-axis, theta x is negative. So it's saying, I think this is 0.5, minus 0.5, whatever it is, right? And currently theta y is parameterized to take a positive action. That's why it exists, above the y-axis, above that y equals 0, right? And that's the current policy. Now, suppose we have a data point. Remember, we have that static data set of experience, B, and that's all we can learn with, right? We can just learn from the data that we see. Suppose this data point is some sort of action that X took in the past, AX, and some sort of action that Y took in the past at the same time, right? AY. But this action that we see, our data point, is that X took a positive action, right? AX is positive, and AY is negative, okay? So that's this bottom quadrant. We can kind of understand. So we have this policy, and we have the data point, okay? And the idea is of BRUD, when we're trying to learn multi-agent coordination from static data alone, what a lot of the algorithms do, and it's kind of to stay coupled to the data set, is they say, what is the best response for each agent according to the data, right? What is the best response? So given the fact that we've seen AY, for example, what is the best way we change what X has done, okay? And similarly, to change Y, given what we've seen X. I don't know if I got that confused, but I hope that makes sense. So let's look at what that might look like. So this is happening kind of simultaneously, but we deal with one at a time. So before we saw the data point, we saw the policies. If we are X, right, we are now trying to essentially update theta X. That's all we're doing with kind of like when we're updating a deep neural network, right? We're just changing the parameters to kind of optimize some sort of objective. So here we're trying to change theta X. Should we make it more positive? Should we make it more negative, right? And to do that, we're looking at AY, because that's our data point. And we say, okay, well, currently I'm agent X, and I'm taking a negative action. And well, this data point, AY, well, it was also negative, right? And so the best thing for me to do is make my policy more negative. And it's super important to understand this, right? Because what we want to do is move into this region. Of course, we also want to move into that top right region if we can. But given the fact that we're already taking a negative value, a negative action, and Y is taking negative action, the best thing for us to do is make it more negative and actually move in this direction, right? And so theta X actually moves more negative. It's the best response to a negative Y action. Similarly for Y, well, currently we're taking a positive Y action, and we see AX, which is also a positive X action. And we say, well, to kind of optimize that, the best response is to make our policy more positive. And so theta Y actually increases. We make it larger, okay? You can kind of start to see the problem here. So these are happening separately, right? So we're seeing the data. We're saying, okay, let's optimize X, let's optimize Y. What happens when we look at the net update? So there we have nabla J, right? Which is just essentially our what we're trying to optimize. That's our BRUD update, our best response update. Well, we're making theta Y more positive, we're making theta X more negative, and the net vector moves in actually exactly the wrong direction, right? We don't want to go into that top left region. That top left region is bad. It's more negative, right? You can see that. I put there nabla R. We actually know what the true gradient of the surface is. And the true gradient points in exactly the opposite direction, right? And so what this is pointing to is that because our data point and our policy, because they are dissimilar, right? When we try to do this best response under the data set, we actually have a catastrophic miscoordination. not just that we don't learn, but we're actually learning like a very bad policy update. And so I'm going to bring it back to this original thing. We have the current policy, which is there in the dashed line, and we have a data point. And when we do our policy updates, we actually see that we move in a bad direction. Now, there's some nice maths. It's actually pretty simple to follow here, just kind of like first year calculus, to actually show how the gradient field, which is the true gradient field, where we actually want to move, how that actually distorts under the data set, and we actually go into suboptimal regions. But kind of in essence, it comes down to this, is that the X component of how we're trying to update our kind of Q in a typical RL setting, so like our critic, we're looking at the data from Y when we update X. And when we're updating, I think I mixed that up. When we're updating X, we look at the data from Y. And when we're updating Y, we look at the data from X. And that actually creates this problem. Are there any questions at this point before I go forward?
Any like reason why Y can't see what X did? Was that the whole problem? So we want them to be separate, we want them to be isolated.
Right. So like there is this idea, what if we get essentially, we could kind of ignore the data point and just almost like jointly optimize the policy. I think, because then you could like X could also see what Y's policy is.
Y could just see what X is and goes, oh,
yes,
X for negatives, so maybe I should do that.
Yeah. So that is the one thing where like this, I think the abstraction kind of masks what you can do in the real world. And the challenge is we want to stay coupled to that data point. And you can almost imagine that if you're updating theta X based on what theta Y, where theta Y is going, and then update theta Y based on where theta X is going, you can kind of have this like they're leaning on each other, and you become decoupled from the true data. That's kind of the high level hand wavy thing, but I think that there is kind of some more subtleties there. But it's a good question. Yeah.
Maybe a way to think about it is that they're not able to come up with a policy in a sort of centralized way, because although you said they have perfect information about the surface, in a sense they have perfect information about what happens given the data point from one of the other agents, based on what they can do, the variation they can make along that direction. So they don't, in a sense, because if you had the full surface, then you could sort of say, well, each one can just calculate its own, the optimal place, and it'll just move there. Yeah. So in a sense, it's because the only information it really has about the action of agent Y is whatever is in the data set. That's what it's done. And then it can say, okay, what would be the best thing for me to do, given my information, based on that single bit of information about Y. Yeah.
Something I probably should have mentioned earlier as well is the important part of the multi-agent problem is that our policies ought to be decentralized, because essentially in centralizing, you're creating essentially a single agent thing that is like this big controller. So yeah, the fact that we're just conditioning on our own observations, I think is an important point there. Thanks for the question. Cool. So this is going to kind of lead into our solution concept, which is this proximal joint action prioritization, which I'll call PJAP from now on. And it essentially comes from these thoughts. Well, the main reason for miscoordination is the dissimilarity between the current policy output and the sample data point, right? And that's what we saw with the kind of top left quadrant and the bottom right quadrant, right? They're far away from each other, which means that we have this big dissimilarity between the data that we're looking at and our current policy parameters. So we kind of thought, well, what if instead we sampled experience from essentially a data set generating policy? Now, we might not have access to that policy explicitly, but kind of experience from a policy that is more similar to our current policy, right? So the data that we're seeing is kind of more similar to where we are at the moment. And you can kind of understand this quite intuitively. If you imagine you're trying to learn how to play soccer or football, and you have a bunch of 7-year-olds who are learning the game, it doesn't help that you put Cristiano Ronaldo on the field, right? Who, sure, he's very good, but the policies that the little 7-year-olds are playing with is so different to Ronaldo's policy that their learning will be completely distorted, right? And so you kind of want, and that's just like a broad intuition. I'm not saying that that's necessarily the problem, but to give you a flavor for that similarity that we're looking for in terms of what's coming from the data set and what's kind of coming from where our current policy is. Also, a subtlety there would be that it would be like the 7-year-olds trying to learn from data of Cristiano Ronaldo playing, and I'm not going to go too far into that example. And so the idea here is, well, if we want to prioritize something that expands, what if we set priorities? So when we're sampling our data, we prioritize the data that is some sort of function of a distance between these policies. Now, again, the data set generating policy is, we don't have access to the actual parameters of the policy that generated the data set. And so instead, we want to kind of have some sort of metric between the actions that we see and the actions that our current policy is taking. So here's an example. A GIF is nice because it's super visual. So here's an example where on the left, we have a bunch of data points for our XY game. So I don't have the legend here, but the top right and the bottom left, these yellow regions are the high reward regions. And we have a bunch of data points, and the data points are these kind of just circles that are outlined, right? And what that's saying is in our data set, perhaps we have a tuple 0, 0, and then the reward that we got, which was 0. And then we have another one, 0.5 and minus 0.25, and we have the corresponding reward, right? And that's the data that we're trying to learn from. So that's the data set. And what we're trying to do is we're sampling batches of data from this. And these are the ones that are getting highlighted. And at each time step, we're trying to learn where to move our policy. And you can see that MADDPG, which is one of these early MAL algorithms, is really struggling. Okay? And we can kind of understand that because if we cast our mind back to the example before, when our current policy, which is kind of in this top left-hand corner, is seeing data that is very dissimilar from where we currently are, it's going to cause this miscoordination, right? And so you can see we're getting data points from kind of the bottom right-hand quadrant and also the bottom left and the top right, which is very different to what we're currently doing. And you can see if you let this simulation, if you let this training kind of run for longer, it kind of goes nowhere. And you can actually mathematically also show, based on the bias of this data set, you can actually show where it will converge to. But the point being is that it's struggling. And so if I kind of bring it back to this PJAP idea, what happens if we instead of sampling uniformly from that data set, we sample with some sort of prioritization on the things that are close to our current policy? Because we know our current policy, right? And so what that means is instead of sampling uniformly over this grid, we look at where we currently are and we set the priorities to be close to that. And so here's an example of that, where in the GIF where it initializes, it's initializing in the same place and it's kind of walking around a little bit randomly, as we saw before. But then as we start to process more and more of the data, we say, well, let's prioritize the data that is closer to our current policy, right? And you can kind of see this reflected in the samples on the left, okay? That the samples start clustering around our current policy. It doesn't completely converge that we're only seeing points literally exactly next to us. We still want to see.
I'm not quite following what the two parts are showing.
Yes, sorry. So this is on the left-hand side, we have all the data points, which are the kind of thin line circles, right? Those are all the data the points we could sample, okay? And previously what we were doing is we were sampling randomly, uniformly, randomly. Sampling those tuples, right? So like the X value, the Y value, and the reward, yeah.
Not quite sampling the reward function, because that would say that you have access to the simulator. On the left, there's a finite amount of data that has previously been sampled, and that's all you have to play with. And so, first of all, you're sampling from the static data set randomly. So you can't sample from any that you want. You just say, I want to pull out whatever data you have, and you do that in batches. And then the second one is saying, okay, I only want to look at data which is close to my current policy.
Yes. So then the thing on the right is saying, well, where we start there, the red, okay, is our policy, our theta. So that's actually just a trajectory of theta, right? And so red is where we've initialized our policy. It's currently that, X takes some sort of action, Y takes some sort of action. And then we process data. We say, again, where should we move theta Y? Where should we move theta X? And we take that step. And so this is now over time that policy learning of how should we update the parameters of theta based on these sampled data points from the data set. We can
It's just confusing because there's no state. It's like so simple. There's no state space.
there's no state indeed. So this is the time here is the learning, the policy learning, right? So how, like, the discrete time steps here are not discrete time steps in the environment necessarily, right? It's how our parameters are changing over time. It's the learning curve, essentially, the learning of the policy parameters, right?
So one way maybe to think about it, so this is a sort of extension of matrix games like the Prisoner's Dilemma. So imagine that you're playing the Prisoner's Dilemma with somebody else, and the way you're trying to learn it isn't by playing the Prisoner's Dilemma over and over again, but you've got some book of previous games of people's played of the Prisoner's Dilemma. You start off saying, okay, this is my policy and that's your policy. Okay, this is what we're going to get. And now you just sample from that book of previous games of Prisoner's Dilemma, and each of you then updates in one step. Okay, now actually I'll try this thing, try something different. And then you look again in the book and you say, okay, maybe I'll try something different. And that's what each of the steps are here. But in this case, it's not just looking at one game, you're looking at lots of previous games. And it's just that now you've got a continuum of actions rather than just two actions.
With the prioritization, your example changes to you're looking at the book, but you're looking at the book of games that were at a similar level to you.
Exactly.
Now, if you start, let's say you don't start nicely there in the middle, sort of, what if you started in the top right, and now it prioritizes points close to it, but let's say this bottom left is way better actually, more yellow than this top right. It does the starting point now and the prioritization together result in, you go into the top right.
It could, right? It could. And it's hard to say without kind of the concrete example, but the key is here, we do have another hyperparameter, which is how sharply do we want that prioritization to cut off? So you can imagine in that, the book example, do we just look at the same example over and over again? Well, we're not going to do any sort of learning. So we want some sort of difference between our current policy and the data we're seeing. We do want some sort of distance, but then the further out we go, kind of the more dangerous it is, right? And so that is indeed another hyperparameter and something that perhaps, we want to find maybe a solution that's more auto-tuned, but in this case, we're tuning that hyperparameter. But it's a great question. Are we happy with that?
So like we were saying like one data point, it's just like what fix why the things why do what did and I average
Yes, sorry. I think that's I probably am a little bit unclear in this GIF in that we're sampling batches. So we're sampling over the batches of data, and what we would see actually is we were just sampling a data point. It would be even more kind of just like all over the place. But that's just we're processing maybe a batch of 64 samples here and then taking the mean theta update. And indeed, so the idea here, the difference between offline and online is that in an online reinforcement learning setting, we could say, hey, what is the reward when X takes this and Y takes that, right? And we kind of have that ability to almost query the simulator and ask the simulator what reward we would get. But now we constrain to just that data set, right? Just the data set of points and looking at those alone, trying to learn from them. So this is MEDDPG, and once again, our policy learning, the key here is that our policy is not going to the right place. Like we're not converging to the right parameters, right? And what I really just want to hit home here with PJAP is we're not just now looking at points exactly where our policy is, but we're just making it more localized. You can kind of understand, you can see how the policy learning almost moves it moves up into the direction, and the batches that we're seeing when that happens, how that evolves as well, right? And we're still getting points kind of from other parts of the grid, but there's a little bit more of like a bias towards where we currently are, right? And indeed, the wonderful thing is that we see that we converge to the high reward region, right? And that's really the essence, is that just with this kind of subtle shift in terms of looking at data that's more relevant to where our current policy parameters are, we're able to learn the optimal policy. And what's also fun here is that we see that we can see in the beginning that we're sampling kind of uniformly, but as we see more and more samples, we start prioritizing the samples that are closer to our policy. And yeah,
maybe something to add there. So it sort of looks like as you're getting closer towards the optimum, you're actually looking at points further away. So like over there, you're looking at points further away. That's only because you're constrained there to only look at points. So when you're very close to the top right, you can't look at points further to the top right, which you would do if you had a sort of uniform sampling.
Yeah.
So to get 64 points, you have to look further away.
Yeah, I think that is important. And what would maybe be useful for this grid is actually to not plot it from -1 to 1, but zoom out just a little bit and you'll just see a little block of points, right? And that's essentially what's cool. And kind of what's happening in the buffer underneath. And so when I say buffer, these data points are going to be stored in some sort of data set, right? And when I say prioritization, the idea here is that a priority of 1, say everything had a priority of 1, we just have uniform sampling, right? But we could make some priorities lower and others higher, and it's more likely that we'll sample from them. So this is kind of a common idea in reinforcement learning. And this is just a visualization then of how those priorities change during learning, right? And so in the beginning, everything's red, very briefly. So we initialize that everything is uniformly likely to be sampled, right? And then as we start seeing more and more data points, we say, okay, well, how far is this data point from our current policy, and set the priorities accordingly. And we can kind of see these gifts don't move in lockstep, unfortunately. But you can kind of see how we localize around the policy, we prioritize seeing those data points, and then we move along with it. Now, it is important, as I mentioned earlier, in this previous GIF, it is important that we still see data from kind of elsewhere. And that's what's quite nice about a prioritized approach, is it doesn't mean that it's impossible to sample, I don't know, this point here, just because it has a lower priority. It just means that in expectation, we will see things that are closer to our current policy. And that steepness of the prioritization is also important as a hyperparameter. Just going to bring back this text from earlier. So the main reason for the miscoordination is the dissimilarity between the current joint policy and the sampled action. To kind of verify whether or not this is actually happening, right? Here's an example where we look at the distance between our current policy and the sampled actions, right? Because we're saying previously these things were super dissimilar and that caused the problem. Well, here's an example where in orange, we just have MNDDBG, right? So we are sampling points uniformly across the grid with that previous example. And you can kind of understand then that the mean distance between our current policy and the points sampled is going to be fairly constant, right? Because wherever we move, we're kind of just sampling uniformly in that grid, right? Not exactly, but you kind of get the idea. Whereas with PJAP, indeed, what we see is that the distance between our sampled points and our current policy decreases. Okay, so this is just saying PJAP is doing what we think it's doing, right? How does that impact the reward? Well, we see this clear, right? So we see this corresponding thing whereas the orange kind of plateaus at some sort of reward, with PJAP, we actually achieve a higher reward. And that's just kind of affirming with that the distance is this important part, and making our sampled actions more similar to our current joint policy yields benefit. Here's an example in a more complex polynomial game. So we were talking earlier about like a different game, and it's really fun because now we don't have to just do X, Y, right? And there are all sorts of fun things in the paper where we've defined these other games where miscoordination can arise. This is called the Twin Peaks game. And the idea here is, I should have actually put the 3D plot. It's these two peaks kind of in the top right and bottom left corners. And here's our data set on the left. And in blue, that kind of policy learning is just vanilla MNDDBG. And we can actually show here that it falls apart. Mathematically, there's also this kind of like nice analytical result to show that the miscoordination happens. And indeed, with PJAP, we can see this third plot here is, again, the distance, the mean distance. That mean distance is lower. On the trajectory plot of this policy learning, we can see that we get to our optimum and the sample efficiency, essentially our return plot, we also see higher performance. So this is just showing that kind of success in a more complex game. And with this kind of key idea being that the lower the mean distance between the sampled actions and the current policy results in better performance. Now, this is still in a polynomial game. What happens when we try it in a more complex scenario? Now, it does get more complex with, say, this example on the top right, which is 6 half cheetah, 2 half cheetah. It's the half cheetah from Mujoku. And what we're trying to do here is get this cheetah to walk. Now, of course, it's a lot more complicated there. Our action space is of high dimensions. We have state as well, and all sorts of other things. But even just in this kind of simple thing where we're transferring idea of PJAP with kind of a naive distance metric, we see this improvement. So the graph there is showing the mean distance between the current samples and the current policy, right? And so have I labeled it? Oh, the blue at the bottom here. So the blue is with PJAP. So we see lower distance as we saw before. And indeed, in this performance plot, we see that there's statistically significant better results. And all that's saying is this is not the finalized PJAP. This isn't definitively how it should perform in kind of like more complex scenarios. We really think that there's a lot of research to be done in terms of like better distance metrics and whatnot. But even just the simple idea from the polynomial game, transferring it kind of exactly as is to this more complex scenario leads to better results, which is a really, really encouraging result. I think what was most fun about this research is that because a lot of it's in the polynomial game, very simple, tractable context, it can all be run in browser, right? You don't need a GPU. You can literally run this right now in a Google Colab notebook with CPU because these games are super simple. And there's also this analytical component that's tractable. And you can't just look at a result that doesn't agree with what you think and then be like, I don't know, it's noise or something. It really forces you to ask good questions about your work. And so that was really fun about this work. And I think that's a really nice foundation for future work in building on these polynomial games. And yeah, just some conclusions. So these polynomial games we feel are super useful for understanding actually more complex phenomena, but in a tractable and kind of interpretable way. Importantly, miscoordination in this best response setting, which appears a lot in offline MAL, it can be solved through dataset sampling prioritization. And then just as a nice kind of additional point is that doing this doesn't change kind of the other techniques you can use in offline MAL for regularization, such as critic and policy regularization. So it's just like another tool in your toolbox. And yeah, this essentially was a paper that I worked on with Claude, who's a member of the Shocklab as well. Louise, one of my colleagues at InstaDeep, Prof. Shock, and Anu Pretorius as well. And this was at an ICML workshop and is also under review at a main track as well. So yeah, I'd love it if you took a look at the paper, and if you have any more questions, please do ask. And we're super excited for kind of more research stemming from this, more principled, simpler in a sense, simpler problem setting, but actually leads to kind of more complex solution concepts. Yeah, thank you.
Fantastic. Cool. Thank you, Callum. Any questions, everybody?
So what's the intuition of the sample efficiency being so much better?
So you're talking about this plot here?
It seems that there's also, in all scenarios, it seems to either perform as well or out.
Right. So the sample efficiency, I think, can sometimes be a misleading title, or and essentially that's just your return, like your reward, your graph, your performance. And it's just saying here that we can achieve higher performance, which in this trajectory plot is just saying we can get to a more yellow region in the thing.
See, that makes sense. Because I thought if you sample with 64, about 64 each time, let's see why.
Yes.
You're more efficient.
Sorry, yeah. I think that the misnomer there is maybe the sample efficiency. It's used to, I think, talk about these return graphs, but you can just think of that as the reward over time. Yeah.
Can this just be seen as like a curriculum, like an automatic curriculum? And if so, have you compared that to like more classical, curriculum?
I'm not too sure. I don't know what you think, John.
Yeah, I mean, I think it's a form of curriculum learning. I think the difference is that curriculum learning has mostly been studied in the online single agent case, where there is sort of it's easier to have a sort of teacher-student network type thing. And indeed, I think it would be interesting to look at training a teacher to do the prioritization. But I think the difference really is that the miscoordination problem here is a function of it being offline. And so I would guess that traditional curriculum methods, I don't know how easy they would be to implement in offline ways. Although I think in a sense it is a form of curriculum learning where that prioritization is just saying, okay, you want to take actions close to those that were already taken.
For sure, and I guess also your set that you're choosing, your training set, because you're something based on your prioritization is based on the similarity between your current policy and not necessarily the performance. Because if you were to sample based on performance, you might be sampling in different locations. And that would also cause the same. Because you have those two regions. So
exactly. I think that example actually is kind of more aligned to my silly example from earlier, which is the Ronaldo thing. That if you're just sampling things that are really good, it doesn't necessarily mean it's going to lead to good learning as the team. And it's one of these challenges of multi-agent problems is that there's almost this joint policy learning that needs to happen, which means that one can't just be really, really good and the others kind of fall behind. Yeah. Interesting ideas there. And just with respect to kind of the link to online, we've dealt with it more in the paper, but there's actually this nice plot showing why in the online case this doesn't happen. And essentially, as you move more off policy, you get closer to the problem. And offline mile, I think it was a fairly novel formulation, was actually viewing it as a spectrum and offline mile just sitting at the edge of that spectrum. There's another question from Tim, which I'll read now as well, and it's going to relate to something in the paper. So I'm just going to actually show the paper, and then I can also show that graph. So Tim, can you still see is my oh, it's paused. I see. Let me just share the right screen quickly. That's important. I'll just share this. Cool. So this is the paper itself, and just to kind of mention this online versus offline thing. So here's an example where we actually do it online, and this bottom row is showing the state of the replay buffer at the final training step. And what we're saying is that as we increase the size of the replay buffer, we have more stale data, and so more possibility of miscoordination. And the way that the online case solves this is that because your data is being replaced in the replay buffer over time, you naturally have almost this regularization to data that is close to your current policy because you're generating the data as you go, right? And what's really interesting here is that a lot of people find that like a large replay buffer doesn't work in multi-agent reinforcement learning in the online case, but no one's really thinking about why. It was just kind of like, oh, well, this doesn't work. Let's just make this a hyperparameter. Let's make it smaller. And I think that it's dangerous to just see it as a kind of spurious hyperparameter that, oh, we just make it smaller. I think one of the problems is that this miscoordination arises as you make that buffer larger. But making it smaller is also not necessarily good because we want to leverage the off-policy data, right? And so I think that that's also an important step in the online research space.
I think the question from Tim was
yes.
The distance metrics.
Yeah, so let me just read out that question for the yes.
Could you chat a bit more about how you calculate the distances required for PJAP?
Cool. Yeah, so the distances, one of the important things before I go on is that we wanted to kind of highlight that PJAP is more of a solution concept, and then there are instantiations of PJAP which relate to the specific distance metrics that you use. And the hope there is that we usher in kind of new formulations of PJAP that lead to kind of better properties and qualities and stuff. And so we're not saying that this, distance metric is necessarily the thing. It's saying if we could prioritize samples that are closer to our current joint policy, we would get this benefit. And here's a couple of examples. And so in the paper, for example, here we have essentially one of the PJAPs, which is kind of, we transform the distance on a Gaussian. So the distance there is d, and so the e to the minus alpha d, and that d is between mu k. Sorry, I'm kind of, what's the best way for me to do this? Mu k is our current policy, and then beta tau is kind of our sample data, which we don't have access to the parameters necessarily, but we have some sort of distance metric of that, and then we transform it on this Gaussian, and then we clip it, which is just this max between that and an epsilon. And then what does d look like? Well, d could, for example, be the L1 distance, and here we have the distance between mu k and beta tau. We define that as our sampled actions, which is, we sample, yeah, there we go. We sample a hat from the dataset B, and then we calculate the L1 distance between that. And I mean, even this, I think, is a little bit incorrect, where it's not that we're actually measuring the distance between that and the current policy parameters. We actually want to see the action that the current policy parameters spit out, right? So that we're comparing actions with actions. In the polynomial game, the benefit here is that the policy is the action. But in the more complex case, like MMUJOKU, here we now have a trajectory of data in each of our samples. And so we then sum over the trajectory and we sum over the agents, and that's how we calculate our distance. But indeed, the hope is that you walk away from this thinking, oh, I want to come up with a better distance metric for PJAP, and that it spurs on some new ideas there. Thanks for the question, Tim.
Any other questions? Okay. If not, thank you very much again, Callum. Wonderful.
Thank you very much.